All right, happy Thursday. We're going to look at sections 8.1 and 8.2 today. Our 8.1, we're going to talk about a distribution of sample mean with a normal population. Really briefly, we'll talk about the distribution of sample mean with a non-normal population. And then we're going to look at sampling distributions of sample proportions and compute probabilities with sample proportions. So that is where we're going today. I really love where this lesson is kind of a precursor for chapter 9 and chapter 10. And so it kind of lays some groundwork for some super fun stuff. Yes, it's fun. I know you guys don't believe me, but yes, the stuff we're going to is fun for me, hopefully for you. So this, I mean, I don't know. I don't think it's too bad. I don't think today's too bad. So I will let you know when we switch over from 8.1 to 8.2. When we do switch from 8.1 to 8.2, you're going to take 8.1 and you're going to put it on a shelf, take a deep breath, and then clear your mind so that you can get into 8.2, hopefully without any confusion. So that's where we're going right now. All right. So what a sampling distribution is, and what we do is we take, and I have an example in a second, but what a sampling distribution is we pick a sample size. So sample size 5 or 10 or 50 or whatever. And in a population, we would take all of the possible values of that sample size. So I would be like, I have a population of 100,000 people, and we would take sample sizes of 50, and we would find the mean of each of those sample sizes, each of those size 50 sample sizes, and we would just keep doing that until we got all of the possible samples out of there. So a sampling distribution would be taking all of those samples, all of the means that we found, and we will be analyzing just all of those means. That's what the sampling distribution of a sample mean is. And because we are dealing with samples, we will be using X bar, because remember, X bar is a sample mean. And I'm going to get more detailed, but this is just giving you some vocabulary. And this is not vocabulary that's going to be on a quiz. So you don't have to memorize this stuff. All right. So here's an example of what I'm talking about. So the government wants to figure out the mean income of all of the households in the US. We can't sample every single person. We can't. We don't have that population mean because we would have to sample every single household in the US. That's just not possible. So what they did was they took 250,000 randomly selected households and they found the mean of that income. And that's right here. And then they would take another simple random sample, and that's this mean right here. And then they do a third one, and that mean is right there. So now our sample means are going to vary because every sample has different people in it. So they're going to vary a bit. And it's a random variable. So our sample means are all different, but what we can do is we take a whole bunch of these means. So if I kept sampling 250,000 households and finding the mean of those, then I can take all of those means and use those as data values. And if I find the mean of those means, it should be getting closer to the population. And it just makes it a little bit easier to not sample every household in the whole US. So that's basically what's happening. All right. So you don't have to memorize the steps, but this is basically how we would do sampling distribution. So the first thing you would do is you would find the simple random sample of size n, whatever that is that you've chosen. And we will talk later on, probably in chapter 10. I think it's chapter 10, where we determine what sample sizes are good. So don't worry about trying to discover that right now. Then you find the mean of that sample. And if we have a finite population, we keep doing that, keep taking a new sample, then compute the mean, take a new sample, compute the mean. We keep doing this until we get all of the possible simple random samples. As this says, once we have a certain sample, you can't take that sample a second time. We just keep doing this until we have all of the possible samples. And that's going to give me a whole lot of means. And then those means become my new data values. And hopefully as we go, it'll make a little more sense what's happening. All right. So we have weight of pennies minted after 1982. They're approximately normally distributed. They have a mean of 2.46 grams and a standard deviation of 0.02 grams. So we took sample means, 200 simple random samples of n equals 5 from this population. So we took 200 samples. So basically, I took 5 pennies 200 times, and I found their means of each of those 200 samples. So for example, this is one sample of n equals 5, and I found this mean right here for just this sample. So I would just keep doing that. I would keep randomly selecting samples of 5 pennies and taking their mean. And I'm recording their mean each time. These are all the means. Don't worry, I'm not going to make you do anything with them. Just showing you this is all of the means from samples of size 5. So now that I have all of these means, I can arrange them into a histogram and I can see how the means are distributed. In just a minute, I'm going to show you that histogram. So my standard deviation of all of those means, you're just going to have to trust me, is this 0.0086. It's a really small standard deviation. This means they're not super spread out. Because I collected all of those means, they're all going to be pretty close together. So take a look. Here is my histogram for my 200 sample means when I had a sample size of 5. This is pretty close to normally distributed. I mean, I would probably call it normally distributed. I mean, it has one big, and I can kind of draw, and that one up here is weird and it sticks out funny, but it is mostly normal. It's not skewed and it's not uniform. So, I mean, I would call it normal. So let's take a look at what role the sample size plays in this. So let's see what happens to my standard deviation as I get bigger sample sizes. So this right here is probably a good thing to write down. It's quite possible there'll be a question somewhere about that. I don't know if it's in the homework or if it is in the quiz. I can't remember, but I know that it does come up. As the size of the sample increases, the standard deviation of the distribution of sample mean decreases. So I'll give you a second. It's a good thing to write down. If you print it off the PowerPoint, maybe just put a star next to it or highlight it or something.
It didn't print on mine.
That's rude.
Yeah, so I'm having to write it.
Man, I gave you extra work. I'll let y'all take a moment.
Oh, it did on the second page. Oh, I just wrote it, so never mind.
All right. All right, can I move on or does anyone need a moment again? Okay. So let's take a look with sample size 20. Let's see what happens. Look at this histogram. This looks so much prettier. It is even closer to a nice, pretty bell curve. And take a look at my standard deviation now. It is much, much smaller. we like small standard deviations. That means that we're getting closer and closer to the actual mean, to the population mean. We can use sampling distributions to estimate that population mean. Because as we get more and more samples and as we get bigger samples, we're going to end up closer and closer to the actual mean. And our standard deviation gets smaller, so our values are less spread out. So suppose that I have a simple random sample and I drew from a large population. We will have our mean equals our mean sub x bar, mu sub x bar. It equals the population mean. So as we get more and more samples, it equals mu. So when you're asked for mean of a sampling distribution, it will equal the population mean. Our standard deviation, we use this right here. You take sigma, which is your population standard deviation, and divide it by the square root of your sample size. So this right here, sample size. This right here, population standard deviation. We call it, you will see it called standard deviation and you will see it called standard error. They're the same thing. Standard error and standard deviation are the same thing here. So I believe the homework kind of uses them interchangeably. They might ask you for the standard deviation of the sampling distribution, or they might call it standard error. So either one is the same, and it's sigma sub x bar. That's how you would read that, the sigma sub x bar. So it's saying standard deviation of the sampling distribution. So, all right. So when we were looking at earlier, we took our population standard deviation that we were given, divided it by the square root of 5, and we got this right here. It is really close to what we found. We found this. This is what, by actually putting all of those numbers in the calculator and calculating the standard deviation, that's what we got. But I don't think anybody's going to be upset by 3 10,000ths difference. I don't think that's going to make much difference at all. I would just rather use this formula than put 200 things in my calculator. I think you would all agree with that, because it's close enough. And my open math is going to require you to just use this formula anyway. So now when we are looking at simple random sample of n equals 20, we took the mean, or I found the standard deviation of all of those. Using the formula, I got this. It is exactly the same thing that we found by putting it all in the calculator. So it's exactly the same thing. So definitely just use the formula, since they're not going to give you all the data anyway. Questions so far? All right, we're going to math some things out. We're going to math some stuff. I like some good mathing. Okay. If our random variable is normally distributed, then the distribution of sample mean is also normally distributed. This right here, you might want to know this. Oops, leave that there. Sorry. So if our random variable is normally distributed, then the sample mean is normally distributed, or the distribution of the sample means. It's always so much easier when we're dealing with a population that's normally distributed. When things aren't skewed, it's so much easier. Okay. So here's an example. An intelligence quotient, or IQ, it's a measure. What measurement says that? Measure of intelligence derived from a standardized test. The scores are normally distributed with a mean score of 100 and a standard deviation of 15. We have a population with a sample size of 9. So we are looking for our mean and our standard deviation with a sample size of 9. So remember, our mean, our mu sub x bar, is the same thing as our population mean. So our mu sub x bar equals 100. We just use what they give us for our population mean. Easy as that. So our sigma sub x bar equals sigma divided by the square root of n. So our sigma, standard deviation of 15, divided by the square root of n, square root of 9. So 15 divided by 3 is 5. And I bet you dollars to donuts when I swipe, it's going to have all of that math done without me. Nope, it wasn't there. So our standard deviation for our sampling distribution is 5, and our mean is 100. So remember, this is the mean of all of the means we collected, and this is the standard deviation of all of the means that we collected of our samples. All right. Questions before I move on? I have another example, I believe. Okay. Okay. So we will need to find the mean and the standard deviation. That's the first thing we're going to do here. The weight of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02. We took a simple random sample of 10 pennies minted after 1982. And we're looking for what is the probability that the sample mean is at least 2.465. Second, I got to get my calculator. All right. So the first thing I want you to do is I just want you to find the mean and the standard deviation or standard error. So I want you to find the mu sub x bar and the standard deviation sub x bar. Then we'll do the rest of it. So just like we did on the last one, find your mu sub x bar and your standard deviation sub x bar. So take a moment. So this I got. How'd we do?
I did not get 2 zeros. I got 0.0632.
Did you put 0.02 for your numerator?
I put 0.02. Do I have to put the zero
No,
before?
no. So it should be 0.02. 0.02 divided by the square root of
Oh, I
10.
didn't do the divided by. I
Yeah.
just did the square root. Okay.
Yeah, divided by. That makes a difference.
I guess so.
Did you get there?
Yeah, I got it.
Okay, good. All right. Thankfully, we are jumping back to previous tools. We are not using the previous calculator function that shall not be named. You know, that Voldemort calculator function, we're not going to use that. However, we will be using normal CDF. We want to know at least 2.46 grams, so it's 2.465 or greater. So we have 2.465, 1E99. The mean is 2.46. The standard deviation is this one right here. It is the one you just calculated. So go ahead and normal CDF that in your calculator. At least normal CDF one isn't the one it's not the scary one. At least I don't think that's the scary one. So what we found out, there's approximately 21.37% chance that the sample mean would be 2.465 or greater. That's what we determined. I do want to show you real quick. I'm going to pop over to my calculator because you know me, I like to show you guys fun calculator tricks and tips. So on my calculator over here, so I'm going to go to my normal CDF. So all this stuff's going to be normal, 2.465. Upper would be 1E99. Okay, my mean was 2.46. So the tip that I want to show you, you can do math in these things here. So I can just do math right here. Uh-oh, what did I do? Okay, I could do 0.02 divided by the square root of 10. I can just put that math right in there. I don't have to do it on my paper. I can put that right directly in those boxes. And I should still get, it's probably even more accurate because I didn't round anything. It's a little bit more accurate. So you're more than welcome to do the math directly into your calculator like that, if you choose to.
And you did that math under normal or under the standard deviation part?
Yeah, because that was the, oops, where is it? Come on. I wanted to go down to normal. There we go. Why isn't it doing it? Okay, hold on. Yeah, it does the math for you. So when I go back in, it usually shows me the actual calculation, usually actually maths it out, but it is doing the math right there for you. And you can put math, if you have math that needs to be done, you can put them into any of the boxes and it does the math for you.
Oh, that's cool.
Yeah. Okay. And it's just less rounded here. All right, let's go back over here. Okay. This was all of the stuff that we just did. Except for the fact that I lost some equal signs. And this should be mu, this should be sigma. Yeah, I don't know why it does that. Okay. I thought I fixed all of these. I guess I didn't. So yeah, it's just showing you. We're looking at the greater than, so it shaded the greater than there. And we got this lovely, this was with z-scores. And it was a little bit different when we put the numbers in here. But I don't understand why they turn everything into z-scores. My curriculum at the high school does it as well. I just feel like you're more likely to make mistakes if you keep converting it to z-scores and back to regular scores and all of that. The more calculations I have to do, the more likely I'm going to make a mistake. So I just like to keep regular values, forget about those z-scores, and just move on. So unless it specifically tells you to use these scores, don't worry about it. Questions? Not too bad so far? Okay. Okay, here's another example. I would like you to try this one. So the IQ of humans is approximately normally distributed. The mean is 100 and the standard deviation is 15. We want you to compute the probability that a simple random sample of size n results in a sample greater than 110. So we're computing that our X bar is greater than 110. So go ahead and do all your calculator stuff. Find the mean and the standard deviation / standard error. And go ahead and we will. Is that what you all got? I could have put it in here wrong, but let's see. Oh, it looks right. Oh, you got 9. Did you do greater than?
Yeah, because it says more greater than 110, right?
Says that it has a mean greater than 110. Let me see here. Did I do it right? So I have 110 is my lower, 1E99 is my upper, 100.
Wouldn't 110 be your upper?
No,
No.
it's greater than, so it's 110 or bigger. So you
I
need
did-
to do 1 minus.
I did it backwards.
You did it backwards.
Yeah.
So yeah, you have the complement of the truth or of the other answer. How'd the rest of y'all do?
I didn't even get the equation because I just got confused. Does the P parentheses mean is bigger than 110? Wouldn't that mean that the 110 would be in the lower bar because it's the lower fence?
That's what I have right here.
Oh.
Yeah.
So
Yeah, this is the probability that X bar is greater than 110. So I have 110 to have 1E99. So 110 is my lower value, and then infinity is my upper value because it's greater than 110.
okay.
Yeah, so if I drew it, that was really ugly. This right here is 100. And then 110 is way out here. And I'm looking for this probability over here. That is the ugliest normal curve I've drawn in a while. It looks like a wave. It is the drunk normal curve. All right. Any other questions? What was that? Any more questions? All right. We can move on then. Let's go to the next screen. All right. So here I have a population that is not normal. This population is not normal. It is just a uniform distribution because the probabilities are the same for each value. And this is another great reason why we can use the sampling distribution is because we can make it normal. Using sampling distribution, we can actually make this, well, we can make the distribution of the sample means become normal. So here we go. So let's take a look at what happens. This is, I took the simple random sample, 200 of them, of n equals 4. So basically what I did was I rolled a dice 4 times, found the average of the number on the dice. Then I did that again, and I did that 200 times. I found the average value of the rolls, and I did it 200 times of 4 rolls each, and I found those averages. So remember, this distribution right here is not normal. So I'm going to roll the dice 4 times, take the average, roll it again, take the average, and continue on and on and on. So take a look at these histograms and what happens as I continue rolling. So first, sample size 4. Sample size 4, this is, maybe it looks like it might be slightly skewed to the right, but it's not uniform by any means. Let's take a look at sample size 10. This one is looking pretty normal. It is nice bell shape. Let's look at sample size 30. That is like almost a perfect bell shape. So as my sample sizes get larger, my non-uniform or my non-normal distribution, the sampling distribution becomes normal. So this is it right here. This right here, the central limit theorem. I don't think I'm going to require, I don't think anything asks you to remember the terms central limit theorem, but this stuff inside of there, it's quite possible there's something on your quiz for that. I can't remember, but it's possible. So as the distribution of the sample mean becomes approximately normal as our sample size increases, and it does not matter the shape of the population. It could be skewed right or left, or it could be uniform. It does not matter the shape of the distribution. As my sample sizes get larger, the distribution of the samples become normal. So I'll give you a minute to write that down if you need to, and then we will move on. I believe the next slide is 8.2. Right. Am I? Nope. This is not, we're not at 8.2. We have another example. I forgot that we were here. Okay. So suppose that the mean time for an oil change at 10-minute oil joint is 11.4 minutes with a standard deviation of 3.2. If the random sample n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. What it means by describe it, it just wants to know our mean and our standard deviation. So go ahead and find those mean and standard deviation. This is a good example. All right, did we all get the same mean and standard deviation? Are we good here?
I'm confused. How did you get 11.2?
Because, oh, it should be 11.4, sorry.
Okay, thank you.
Yeah. So I guess not, well, for some reason I glanced at 3.2 as I was writing 11.4 and things happened. Okay, thank you. All right, so we have 11.4 and 0.5409 approximately. So now we want to know if we have that random sample of 35 oil changes, what is the probability the mean oil change is less than 11 minutes? So it's the probability that X bar is less than 11. So go ahead and calculate that. I went off the edge of the screen. How'd we do? Did we get there?
I got the same answer. Yay.
Yay! Yay!
Yay.
All right, questions. I believe this is the last example with mean. So I want to make sure that we're there.
I'm not ready yet.
Okay.
Sorry.
No, it's okay. Let me know if you get there or if you have a question or need help or explanation.
Yeah, I don't know why I'm not getting the same answer as you.
Did you-
I'm putting, lower bound is -1E99, upper bound is 11.
Okay,
11.4. Oh, I put the wrong number in. I think what
But-
happens is, so when I go to calculate with my upper limit
uh-huh,
as infinity, I just put 10,000. And when I put -10,000 in my lower limit, it gives me the wrong answer. So I have to like clear out and make sure that the calculators, so I don't know why it allows me to put like 10,000 in the lower limit. Or I don't know if that's making sense. I get
Yeah. You are making sense. Now that's why I always just do 1E99 because it's consistency and negative and positive 1E99. So I used to just put 1 and then a whole bunch of zeros. And then sometimes I got weird stuff happening. And so I just switched to 1E99 and it seemed to solve any issues that I had.
And so the E that you use isn't the regular alphabet E. I've seen that you use the comma E. The
Yeah,
E-
it's the one above the comma. Because
Okay.
what this does is it's putting it into scientific notation. So it's basically saying time. So if I like put 5e to the 4th power, it is, this is 5 times 10 to the 4th power is what that is. So I should get 50,000. So this is just 5 times 10 to the 4th power. That's what that is.
I think it was working for me before because I was doing the alphabetical E.
Oh, yeah, that could be the problem.
And so then I realized I could do just 1 and 0, 0, 0, but like you just said, sometimes it gives you the wrong answer.
Right. And so, yeah, use the E above the comma because that is the scientific notation E. Because you notice that sometimes you get answers that look like, sometimes you'll get something like 2.46, like something like this. And then it has like this. And then sometimes it looks like this when your answers. This is 2.4567 times 10 to the negative fourth power. That's what that number is right there. So it's actually, oops, it just gave me that. It didn't actually. So if you'd have to move your decimal point 4 places to the left to get the actual number. So that's what that is. That's scientific notation. I'm going to use an easier number here. 2.3, that's better. E. Now I can do -3 to the negative third power. So watch. It just moved the decimal to 3 places to the left. So it's just funky scientific notation. All right, go back here. Are we okay? Are we good now? Holly, did you get there?
Thank you so much for clarifying all that for me, because I was always, even when I got an answer with the E at the end, I was like, what does that even mean? So just move the decimal over.
Yeah, if it's a negative number, you move the decimal to the left to make the number smaller. If it's a positive number, you move it to the right to make it bigger.
Thank you.
You're welcome. I bet you there's others in this room that didn't know that. So this is a good thing. All right. So now we're in 8.2. So I want you to take the 8.1 stuff and I want you to just put it on a shelf. Just put it on a shelf and just wait until you do your homework, because we are now going to shift to looking at proportions rather than the mean. So it's going to look a little bit different. So just put that on the shelf and, give it a bowl of water or something and let it sit over there and simmer. All right. So now we're in 8.2. We're going to talk about population proportions. So we're going to be doing basically the same thing where we're taking a lot of samples. We use these mostly when we're using categorical data. So we're looking for characteristics of things. So saying like how many people are smokers or how many people have yellow dogs or whatever. So this is used for categorical data. Don't worry, I am not going to use that evil word. We are not using that. We're sticking with normal CDF, but I'm just letting you know. So we've kind of looked at p hat before, but I don't think we called it p hat. So this symbol right here, the P with the little chevron over top of it or caret over top of it, it's called a p hat. We calculate p hat by taking the number of individuals that have a certain characteristic over our sample size, and that gives us p hat. That tells us this proportion of the population or of our sample has that particular characteristic. It's called p hat. It's called a point estimate. In your homework, you'll either be asked to find p hat or you'll be asked to find the point estimate. It is exactly the same thing. We use the point estimate to estimate a population proportion. We're trying to estimate what the actual population is, proportion is, but we have a sample. So p hat is your friend. Give you a moment. Okay. It'll move on now. So a Quinnipiac poll conducted in 2008, 1,745 registered voters. They asked whether or not they approved of the way George W. Bush was handling the economy. 349 responded yes. We're going to get a point estimate for the proportion of registered voters who approved of the way he was handling the economy. So we just take the 349, which is those who said yes, and divide it by our sample size. So 0.2 people, or that proportion of people found that they approved of how he was handling it. So about 20%. That is a point estimate. It is p hat. And p hat is going to remain our friend for the rest of the pass. Give you a moment. We'll move on. Parts per whole, yes. Parts per whole, exactly, Holly. Perfect. So this is the same way we did. Remember when we did relative frequency? It's the same thing. Same thing as relative frequency. They just gave it a new name. They like to do that to us. So I would like you to find this point estimate here. So we asked 1,000 adults, 18 or older, are you currently on some form of low carbohydrate diet? Of those surveyed, 150 said they were on a low carb diet. So go ahead and find that p hat. So we have 150. Oops, should have 150 over 1,000. I know I can do this in my head, but lately I don't trust my in my head math. I mean, I guess it would have been really easy. I just cross out the 0 and then I have 15 hundredths, you know. Your head hurts. I'm sorry. But if you talk to a psychology professor, they will tell you that if your head hurts while you're doing math, it means you're making new connections in there and you're learning something. And then, you know, you can just get mad at her or whatever, throw tomatoes. But you can't throw tomatoes at me because I'm on the other side of your computer screen. So there you go. It didn't go over well in that class either. Okay, let's move on. Did we get 0.15? We good? Okay. All right. Once again, we're going to talk about what happens as our sample sizes get bigger. We're going to do some more histograms. So according to a time poll conducted in June 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. So we're going to look at the sampling distribution of sample proportion for different sample sizes. So basically, I'm just kind of giving you an overview. What we do with these, what we generally do is we look at previous studies and then we take our own samples of it and we use the previous study saying, okay, we're believing that their study is true. And then we're going to say, what is the probability that my study is true? And that's kind of what we're looking for with our samples, is kind of almost proving that study wrong. We're going to get into more of that in chapter 10 with hypothesis testing, but that's basically what's happening here. Is you look at old studies and you say, okay, this is the only number we have for the population, so this is what we have to use. So if I took a sample sizes of 10, see here, it's kind of skewed data. It looks like I have an outlier over here. It's not beautiful and symmetric, and it's not what we want to see. So look at bigger sample size of 50. Everything's coming in with, take a look. Standard deviation was 0.160. My mean was 0.426. Got another sample here with sample size 50. Mean is still 0.426. My standard deviation is getting smaller. Notice how everything is compact right in the middle. I'm going to do one more sample sizes of 100. Look at how small my standard deviation is, and take a look at my mean. This is exactly what the proportion was in the original story, the original problem. And my standard deviation is super small, 0.047. So all of my sample proportions are super close to the middle, and it's a really tall bell curve, but it's really close. I mean, we're slightly skewed right, but not very much. I bet you if my sample sizes got even smaller or even bigger, we would have a nice, pretty bell curve. So as with the means, as our sample sizes get bigger, we get more and more normal. So key points here. Where am I? Whoops, went too far. Shape. As the size of the sample increases, the shape of the sampling distribution becomes approximately normal. Our mean equals the population proportion. So our mu sub p hat equals p. And the standard deviation decreases as the sample size increases. These are important things. Give you a second. Y'all are hanging in there great. We are almost done. I have 9 slides left, so we'll have a few examples and some math, but y'all are doing great. Okay. This is how we find this, the standard error or the standard deviation of our sample distribution. This formula right here. The P that we are using is that population proportion. Now, we are approximately normal if this right here, that NP times 1 minus P greater than or equal to 10 came right back to you. It did not go away. It came right back. Our mu sub P hat equals the population proportion, and this is our standard deviation.
So I watched your recording earlier this week for this chapter, and you had mentioned on that one that the shape of the sampling distribution p hat is approximately the normal provided NP yada yada yada. Might be asked on a future test. Is that still the case?
That is still the case. It could be probably a quiz, I would guess, if it is.
Okay.
It definitely might be.
Okay. I just wanted to make sure.
No, that's a great point. I'm glad you said it because now I didn't have to.
I think you're holding out on us, is what I think.
No, I was actually going to say it. I was going to let you all write it down, and then I was going to say,
Right.
now go back and star that or highlight it or whatever you do. No, this is good. Yes, it could very well be on a future test or quiz.
Which part?
This right here,
All of it? Oh,
Yeah.
that little
that little blurb right there.
okay.
Very possibly. May or may not, but it's good to have that highlighted or starred or whatever, just in case. Because many of you may have noticed, I don't know if any of you, I try not to look at names when I'm grading things, because it's mostly because if it's somebody that I've had a lot of interactions with and I'm really fond of them, I don't want to go easier on them than I would on somebody else. I'm more likely to do that than I am to go harder on somebody. I've never graded harsher on somebody because they irritated me, but I have, if I know the name, sometimes been like, oh, but I know they know that because we've had that conversation, and I don't want to have that bias. So I purposely don't look at names. So I don't know if it's anybody in here, but I know some people were Googling things for their quizzes, and Google doesn't always give you the whole story. So you need to use your notes, because I'm going to pull the answers from your notes, not from what Google gives you. Because sometimes what you get on Google is not the whole story. Just FYI. So I'm not saying anybody in here did, because I don't know. All right, moving on. Okay. So one important thing is that when we are sampling, that you need to make sure that your sample size is no more than 5% of the population. The reason this is important is because our sample values won't be independent if we have too large of a percent of the population. So we need to make sure to check that it's no more than 5% of the population. And even if NP times 1 minus P isn't greater than or equal to 10, we still would use this. But those things are good to check, because knowing they're normal or not is good. Moving on. Okay. So we're going back to this time poll in 2008. 42% of registered voters believed that gay and lesbian couples should be allowed to marry. Suppose we obtain a simple random sample of 50 voters and determine which voters believe, or wait, okay, we're going to describe our sampling distribution. And the describing it basically means find the mean and the standard deviation. If I tell you to describe a sampling distribution, that's what I'm asking you to do. Find the mean and the standard deviation. So my next screen, first thing, 50 is definitely smaller than the population of the United States or registered voters. Also, we have this. This is good. We're greater than or equal to 10. So this right here, sigma sub p hat equals this right here. So my mean is 0.42 because remember my mu sub p hat equals p and my p is 0.42. So you just keep that. And then my standard deviation right here, we use the p that we got from our population, which is 0.42 times 1 minus 0.42 divided by 50 and then take the square root. So our standard deviation is right here. This came really close to what we got on our simulation. This one's a little bit smaller, but it doesn't matter. It's close enough. I mean, it's less than 100th, and I think that that's probably okay. It's basically a little more than 2,000ths. I think we're okay with 2,000ths. We're not building a space shuttle here. I'll give you a moment, and then we will do our own mathing. All right. So based on a study conducted by the Gallup organization, 76% of Americans believe the state of moral values in the United States is getting worse. I bet you that number's higher today, but that is what it is. Suppose we obtain a simple random sample of n equals 60 Americans and determine which believe that the state of morals values is getting worse. We're going to describe the sampling distribution. So all we're looking for is the mean and the standard deviation. So our mean, mu sub p hat, equals 0.76. Our sigma sub p hat equals, that's really supposed to be sub, but my p hat doesn't look like sub. Square root of 0.76 times 1 minus 0.76. You go ahead and just put 0.24 in your calculator if you want. There have been other terms where I've gone straight to 0.24 and I've confused people because I know that that's simple math, but sometimes even the smallest little change in things can mess up our brains. So I'm going to put this in my calculator. So I got approximately
I did something wrong.
You did something wrong?
Yeah, I just don't know if I entered it in correctly. I just did square root 0.76 parentheses 1 minus 0.76 divided by 60 parentheses. Should I just put the parentheses around 1 minus 7.6?
So I would do it like this. If you're going to use the 1 minus 7.6, do it like this. So do square root, and I would do 0.76 times, let me see here, times 1 minus 0.76, close this parenthesis, close that parenthesis, divided by, what is it, 60? 60. This is probably how I would put it in my calculator.
Mine just said error.
Yeah, so you probably didn't close a parenthesis.
I did 2 parentheses. Let's see.
I don't know. Or maybe you use the negative instead of the minus.
No. Oh, wait. I did. Oh, I did the same thing. I did the parentheses after the 60. Square root.
Yeah, these calculators can be your best friend or your worst enemy.
Okay, I got the. I
You got
that.
it?
Yeah,
Yeah.
I got it.
All right.
Thank you.
No problem. This is why we do live. I mean, this is what the live Zoom meetings are about. Because you can watch the video and get really close to the same instruction, but we need to have that interaction. I like it.
Yeah, there was one class that I missed of yours, and then I had to go back and watch your Zoom class, and I had so many questions. I was like, I can't ask her because I'm not on live.
Yeah. I love it when people show up also. It makes the class much more enjoyable for me also that you guys are actually interactive. It's really great.
Yeah.
Okay. All right. So according to Centers for Disease Control and Prevention, 18.8% of school-age children were overweight in 2004. In a random sample of 90 school-age children, 6 to 11 years old, what is the probability at least 19% are overweight? So on A, I would just like you to find the mean and the standard deviation. We'll do the rest of it together after that, but it's good practice. Go ahead and find the mean and the standard deviation. So I almost did X bar instead of P hat. Why did you change colors on me? Are we there? How'd we do?
Where'd you get the 0.812?
Told you every time I do that, somebody's like, where did that come from? And you get to the simple, it's the simple math we can't do.
Oh, it's the one. Okay,
Yeah.
oh,
Every
okay.
time.
How do you know how to do that? Is that happen? Do you have to do that on every single problem, or is it just on certain at least?
No, so this right here, it's just 0.188 times 1 minus 0.188. That's all it is. And this is just,
Oh,
yeah, that's all it is.
okay,
I
so
just,
okay.
yeah, I just did the math ahead of time. See, every time I do that, somebody asks that every term. So it's not just you, everybody, every term it happens.
Oh, good.
And it's because you're you're thinking technical about all this technical new math. And so then I throw some like simple math in there and you're like, wait a minute, I can't go back and get the
I'm
simple.
too smart for this.
I always compare it to like a parking lot. So you're in like a parking lot that's completely full. So your parking lot in your brain completely full of knowledge, and you try to put something new in there, something has to leave.
Yeah.
That's how I always think about it. That's why I can't count. That my students at the high school always laugh at me because I'm handing papers out and I can't count. I always give out the wrong number of papers, always. And counting my my mathletes because I'm the mathletes coach, and I can never count them on the bus and get the right number. I'm like, oh, you guys are all here. It's one of those things.
They're probably switching seats on you because they know that they gives you a hard time.
It would not surprise me. All right, so we have this and we have this. So once again, we're looking at the probability at least 19% are overweight. So I don't have enough room here, so I'm going to do it at the bottom. So we're looking for the probability that P hat is greater than 0.19. So that's what we're looking for. And once again, we're going to use our normal CDF. So we're going to use normal CDF. And that's, my lower number is 0.19, upper is 1E99, and then do 0.188, comma, 0.04118. At least you only have to remember the normal CDF thing for the calculator. Y'all get about 0.4806. I'm giving you guys so much normal CDF practice that it's just going to be ingrained in your brains. So question B,
0.4981.
yeah, you got 4981.
Yeah,
Can you go back and look in your normal CDF, make sure you put them in there right?
yeah, it's in there, right?
Did you round different on this number?
On what one?
On the standard
Uh,
deviation?
Let me see. 04118, 04118. Oh, yep, I did. That's
Okay.
what I did wrong.
Yeah.
Thank you.
One tiny little thing can mess everything up, can't it? Okay, so let's take a look at question B. This one is kind of vague and there's more than one way to really look at it. So we took a random sample of 90 school-age children, and that resulted in 24 overweight kids. So it says, what might you conclude? So the way that I would look at this is I would try to figure out what is the probability of getting 24 overweight children. In order to do that, I need to know that P hat. So that P hat would be 24 over 90. 24 divided by 90, which is 0.267 about. So if I find the probability of getting 0.267 or greater, I can see if this is an unusual value. And I think we pretty much can guess that it will be. I'm just going to throw it in my calculator here. The normal CDF. 0.2671E99. Use the same numbers that I already had in there. This should be real quick because we have everything already in there except for that P hat. So you should just be able to just fill in the new P hat. Go ahead and see if you get the same thing that I got there.
So pretty much in all of the equations moving forward, they're gonna have two steps to it. Finding the information that needs to go into the normal CDF and then completing this normal CDF function.
Definitely for this unit, chapter 8, you're going to have to be finding the new standard deviation on pretty much all of them, yes. So we have 0.0275. So that's less than 5%. So that is an unusual value. The what might you conclude thing is totally like you making up a story or something like that. So we could say that either the Center for Disease Control and Prevention is wrong, it is not 18.8%, or you could say that we happen to take our random sample just happened to include overweight children, or maybe it was an area with high poverty, because we know that the healthier food options are generally less expensive or more expensive. So tends to be children in high poverty areas tend to be more overweight. So it could have been just, we happen to get a random sample with a lot of children in a high poverty area. You pretty much, your what might you conclude can be whatever you want, whatever makes sense. I would say that more study is necessary because the Center for Disease Control and Prevention, their number might be incorrect. So I would probably take more samples. So it's kind of just up to whatever you want to state. And I'm probably, as long as it could make sense, I'm probably wouldn't mark you down for something like that. Questions? Right. Oh, look, all of the math that I just did. All the math, except for they did Z-scores. And once again, I'm not real big on using Z-scores for a lot of things unless they ask for it. But converting to Z-scores, it's not going to give you a better answer. So
Is the homework gonna ask us to convert to Z-scores?
I can't remember. It's possible, but I don't think so. I don't think it does. From memory, I don't think it does. I think mostly it's just going to ask you what's that probability or whatever. So I really don't think so. I'm not going to require it on a test. I am so, but it's possible the homework will. But I love Z-scores for what they're for, but I just don't feel that it's necessary to always convert everything to Z-scores.
Okay.
So, all right. So what this says is their conclusion. What did they say? We would only expect to see about 3 samples in 100 resulting in that sample. This is unusual. Yeah, so see that they didn't even really conclude anything. Okay. This is my last slide. I would like you to try this one. I'm going to give you a few minutes. I would like you to try this one on your own. Go ahead and find your mean and your standard deviation of the first ones and use your normal CDF, and then find your new P hat and B and find that probability, even if you don't conclude anything.
Okay, so I got the mean right,
Okay,
but when I went to compute the standard deviation, instead of putting 0.15, I thought it was 0.12.
oh no, so you ended up with something, oops.
Yeah. So
Okay.
what is that 12% there for?
This is when we're looking at probabilities, what is the probability at most 12? So it's 12 or less. 0.12, and then we use 0.15, 0.0326. So this right here is what we use for our P in our standard deviation and in our mean. And then
we pull the
this is
120
the
out of
probability
there.
we're looking at.
Okay, I might have problems with that.
I got my probability was approximately 0.1787, and I ran out of room. Oh, I lost the one. There we go. Good thing it was a one that was easy to put in there. Oops, I don't want 26 in there. What am I doing? What did I do? This erased a whole bunch. That was weird. Oh, it came back. That was very weird. What? I don't know what's going on here. Go ahead. Okay. Normal CDF. Sorry, I keep going off the edge of the screen. And sorry for my cough.
So how do you know for like I know for the normal CDF in the first one it says at most.
Mhm.
So then you would do the lower and then the higher would be 0.12. But how do you know to put 0.2167 in the lower and then infinity in the higher for the part B?
So basically what it is, when I get my P hat, if my P hat is higher than my population proportion, I know that they're saying, hey, this is an unusually high value. So I think of what would be the probability of getting that unusually high value or more. If it was an unusually low value, like let's say that my P hat, this is not it, but let's say that my P hat was 0.03. If I ended up with a P hat of 0.03, I would be like, that's an unusually low value. What would be the probability of getting that or less? So you just got to look at it and say, is that unusually high or is that unusually low?
How do you know if it's unusually high or low though?
Well, I just see it's much higher than 15%.
Okay.
So it's
And-
higher than my 15%. So I'm saying, okay, what is the probability of getting something that high or higher? And like 3%, that's much smaller than 15%. So I'd say, okay, well, what's the probability of getting that or lower? It just kind of goes with, is it higher than your, if it's higher than your population proportion, then you would go greater than. If it's lower than your population proportion, go lower than. We're trying
Okay.
not to capture this. Basically, you're trying
Okay.
in your area, you're not capturing your mean. Does that help?
Yeah, that helps a lot. Thank you.
You're welcome. Any other questions? Okay, so you would conclude something here. So you would only expect about 2% of people to have, there's only a 2% chance of it being that. You could say that we happen to have people that went to a lot of concerts. I don't know. I don't know. You can make something up or just say that that's unusual. Even if you just tell me that's an unusual value, I'm good with that. Okay. Before we go on, there's a couple of homework problems I want to look at because they're the ones that are most common errors that I see or most common questions that I see in the discussion forum. So I want to quickly go over, hopefully I can get there quickly. I get to my open math here. And we will. Now, first I'm going to go to 8.1. Okay. Give me my teacher preview. All right. So this is one that is very common and most common, one of the most common asked questions. So somebody already asked it in the forums. So this middle number here is your mean. And then this number on the right is 2 standard deviations above the mean. So whatever your standard deviation is that you calculate up here, which is the new standard deviation, add it to the mean twice, and that number is going to go in there. And subtract it from the mean twice, and that's going to go right there. All right. And it seems super basic when I say it, but when you get to it, you're going to look at it and say, what do they want in these boxes? So you're just labeling the 2 standard deviations above and the 2 standard deviations below. All right. Come down here. This right here is the most commonly asked question. Okay. I'm actually going to draw this because I think I need to actually work it out. So I'm going to draw it on my paper. Maybe we're going to see if I can draw it nicely on my paper. Second here, my paper, because my iPad is clearly paper. Okay. 148, 147. And they all, I mean, sometimes they're looking for different things, but they gave me n equals 100, and I'm looking for population standard deviation. Okay, I'm going to scooch over to where I drew this. Why isn't it showing? There we go. Here's my beautiful picture. Okay. It gives you the sample size right here. I am looking for the population standard deviation. You may look at this and say, they did not give me enough information. That might be the very first thing you're thinking about. But think about this curve here is your sampling distribution curve. This is not your population curve. It is the sampling distribution curve. This number right here is the mean. That is the mean. This right here is the mean plus the standard deviation sub X bar, which I can't draw it down there. I'm too close to the bottom of the screen. That is the mean plus the standard deviation sub X bar. So we can figure out what the standard deviation sub X bar is just by looking at this. I can see that my standard deviation sub X bar is 1 because 149 plus 1 is 150. Are y'all still with me? Okay. We have a fancy schmancy formula. We have this formula right here. We have that formula right there. I have standard deviation sub X bar. I don't have sigma, but I have that my population size is 100. Now you can just use your fancy algebra skills and solve for sigma. I'll just math it out for you. There we go. So they might ask you for n. They might ask you for sigma. They might ask for sigma sub X bar. I don't know which thing they're going to ask you for, but just use this formula and just solve for the other one. Those two problems that I just showed you are the two most commonly asked questions in this chapter.
Not to sound dumb or anything, but where did that 10 come from?
Square root of 100.
Okay. I'm just making sure.
See, that car left your parking lot.
It did. It did.
Okay. It's all right. You don't sound dumb at all. It's okay. I bet were two people in this call that were like, I was wondering the same thing. And it's also 7 o'clock at night. So no worries. All right. Any other questions we're still on recording right now. Any other questions that for the good of the class on recording? All right, I'm going to stop the recording. Stop recording.